Okay, so welcome to the second lecture by Shiv. So Shiv will be talking, continue the cosmological perturbation theory. So Shiv is supposed to finish at 6 o'clock. So, but Shiv is staying tonight in the campus. So maybe whatever residual issues that remains, please catch him, okay, and get it resolved. That's very important. Okay, so Shiv, please.
Thanks. Koushik. This is where we were yesterday. I'll just remind you, we had agreed that, right? This was the metric for scalar perturbations. And we had agreed that we need to keep only two such functions, right? Psi and phi. The other two can be rotated way, right? I mean, you can get rid of them by coordinate transformation. I didn't prove it, but you can do that. So this is again, another assumption I made, which I did not specify clearly yesterday, was that this is a spatially flat metric, right? The metric has been assumed to be spatially flat. That's why I just written dxi, dxj very casually here, right? So the whole point is I could have written a delta ij here. This section is flat, okay? So if it was k equal to 1 or k equal to -1, of course, this will change. You will have to take this dot product between spatial components using that metric, whatever is the metric, right? Appropriate for the three-dimensional hypersurface for k equal to 1 or k equal to -1 case. But I'm not going to bother about that. I mean, it doesn't change the calculation. I'll point it to you how it changes when we come to it. So this was the metric, we agreed to it. This could be the metric. And our aim is to solve for perturbation equations in this metric, right? And my aim was to just focus on the dark sector, which is given entirely by a single Boltzmann equation. And we'll try to study that Boltzmann equation today. And once I solve the Boltzmann equation, I have to construct energy momentum tensors from those, the different components of it. And then solve Einstein's equation. I stopped at the choice of the momenta, our choice of coordinate system for momenta. So momenta are defined like this, the coordinate momenta. So I'm going to suppress. I'll put a lambda here for the general case, but it could be, if it's a massive particle, I can put a tau here. If it's a massless particle, I have to write some linear combination of that so that it doesn't vanish. I'll just put a lambda here and be done with it. And I've suppressed m here. There should have been an m here. I put it equal to unity. These are the way we define coordinates, coordinate momenta. But our aim is to choose the coordinate system for momenta to solve the problem that we have at hand. So let me first define proper momenta. And we have this relation. This I can write as G00 This is the square of proper energy. This is the square or proper momenta. Right? I'm just putting a square here, even though I put an I here. Is it clear to you that this is actually the square of the proper momentum? Are you confused about this fact? You can ask a question at this stage. Why should this be proper momentum and not P0? What was the difference between the two? What is a proper momentum? Go on, say it loudly, please. Huh? Sorry? What is a proper, so when in general relativity, okay, we are in general relativity, right? I'm trying to define what are physical momenta. Proper momenta are the physical momenta as measured by the co-moving coordinate, right? And the coordinate momenta are not proper momenta. That's what I'm saying, right? So what is the difference between the two? Why is this a proper momentum? Why is this the correct definition of proper energy? Is this what I measure? The difference between these two is fairly straightforward. And I think you should just think about this, that this coordinate momentum, when I want to, a physical quantity in general relativity is the magnitude of the vector in question, right? The magnitude requires a metric. So I can, for instance, define this. This is a coordinate momentum, but this is not a measurable quantity, right? Please go on. Please say it loudly. What should be preserved? That's one way of saying it, right? You can also say I project a tetrad, right? That's another way of saying it, right? But I will simply say, okay, you find the magnitude of that, right? It's correct, right? So this is the physical momentum, physical energy. This is the square of the physical momentum. So you get the relation P0 square and equals to Pi square plus M square. There should be a minus here somewhere, because I will define it with a minus sign. Oh, sorry, this is -1, right? Now it is correct. Now I can take out. So this is the relation, and so proper momenta is defined as Pi. So I don't have to worry about whether it's an upper index or lower index. Proper momentum is defined like this. But I define proper momentum also. I have to put a vector here, right? So I can put a vector Ni up or Ni down, right? This is the direction of the photon. So I can put, now you may say, should I put it up or should I put it down? And is there a difference between the two? I said I have Euclidean space in 3 dimensions, right? If I did not pick Euclidean space in 3 dimensions, I will have to distinguish between the two, because this vector in 3D, right? Its magnitude will have to compute with that metric, but my metric now is delta ij, so I don't have to care about it. So what I will do as I go along, whenever I say lowercase p, that's a proper momentum. I'm not going to bother about whether it's up or down. Same way when I'm going to talk about direction of the photon, I'm not going to bother about whether it's up or down. It's the same, right? Now the task is to compute the relation between the physical momenta and the coordinate momenta, and I will write down a few forms and you can compute the later. So for instance, Pi is you can compute this. This is capital. I think capital, I will put this here. This is lowercase, this is capital. So this is coordinate momenta. So this is the lowercase coordinate momentum. You can work it out. It's fairly straightforward, right? Because from these relations, first you compute the uppercase and then you go with G, then you compute the lowercase. One thing that immediately tells you is, you notice that in the background, this Pi was conserved. Remember that? We worked it out yesterday. The lowercase Pi was conserved in the expanding universe, right? So this is actually, so phi is 0 in the 0th order. It's clear. So Pi A is a constant. So Pi goes as 1 by A. The physical momentum was, so you can actually see that this holds, of course. Why am I doing this? I have to compute this quantity. The volume element of the momenta, that's what I need to solve for the distribution function. This is what? Now I'm going to define another coordinate. And so Qj is A Pi. API is Q, and the volume element I have written it assuming it's isotropic, right? Which it is, the momentum space. So I will use this momenta from this point onwards, right? So dp, but I have to still get rid of this factor of 1 by 1 minus 3 phi. In the same coordinate system that we have defined, I can write Can you see this? You can see it from this formula actually, right? That's the determinant of the metric. And inverse of that, square root, right? Determinant of the metric, you will pick 6 factors of 6 from here, 6 phi, cube of this factor, right? In linear theory, the cube of this factor will give you a factor of 6 here. And this factor will remain. And then I have to invert it and take the square root, that will change the sign. One will come with a minus sign, the other will come with a plus sign, right? So metric is you have to multiply all the factors, and this will give you a to the power 8, remember? 4 times you multiply A with itself, but you have to take the square root and inverse of that, so 1 by A4. That's a metric. Now, let me try to compute this is where I project out the pressure perturbation. This was equal to dp1, dp2, dp3 minus g pi divided by p0 f x. Now I'll write q. Okay, I'm going to maybe I'll try to write eta here. There's a bit of notational thing. I like eta for conformal time in the mind, but Shingar writes tau. So maybe I'll do it off and on. If you find a mistake, you just point it out. Oh, you should have put eta there and not. So I can compute pi, I can compute this dot product is straightforward to compute in terms of q. P0, I have just computed there, right? You can compute P0 from using this relation. You have this, right? So from here, you can actually compute P0. P0 square is, this is Pi square, right? Take it on the other side, divide by G0. So you can actually compute P0. I'll just write down what P0 is. P0 is 1 by A E square plus M square 1 minus psi. This is 1 minus psi. So I'm going to use a slightly different notation now. Epsilon by A square. So epsilon is defined as U square plus U square A square. If this is A, this is E, capital E, for instance, and epsilon is A into capital E. Somebody said something? To the power, have to put the half now. Yeah. So if this is E, this is A into E, so I will define notations, but I'm going to use epsilon in. Okay, now we are ready to compute this volume element, right? We can compute P0, we can compute these quantities. The volume element we have already computed. This metric also we have computed, right? This will, the volume element will turn out to be, and I'll just write it down, 1 by A4, and expect you to check that, 1 minus psi plus 3 phi. Can you see it? And now it justifies. Now, after I've written this form, you'll see why this coordinate system was picked and why this discussion about the coordinate system, right? This coordinate system was picked so that there are no metric element in the volume element of these distribution functions. You see, this comes from the metric, so I want you to actually go through this. This comes from the metric, this comes from the volume element in momenta, right? And when you take into account all of these, the definition of P0 and all of this, they actually cancel out because 1 minus 3 phi, 1 plus psi, right? It will be exactly 1 minus 3 phi plus psi, right? Because higher order terms I'm going to drop. You see, this is first order in perturbation theory. They'll exactly cancel with this. 1 minus psi plus 3 phi multiplied by 1 minus 3 phi plus psi, it'll give you unity in linear perturbation theory, right? You can check it. In linear perturbation theory, this volume element simplifies, and that was the reason why we picked the coordinate system we picked. It's a somewhat subtle point that you see, before doing a calculation like this, one has to take into account the fact that now one has come into first order in perturbation theory, and it's not entirely straightforward, right, to pick these volume elements. So I demonstrated to you that you can actually do it for the pressure perturbations. Okay. Similarly, I will write down the result without proving it for T00. So T00 is, again, I'll write down the form, and now that you are familiar, the minus sign is not there. I think I put it. P0 in the denominator, f of x, q, and theta. You can work it out also. This will cancel with this. There is a P0 sitting here. Again, the same factors will come. And once you're done with it, you will find that it will reduce to exactly the form that you would expect. Q square dq 1 by a4 d omega. You can show that in this case. Oops. Silent here. So please show that this volume element reduces to this. Okay. We have already done that for the pressure case. Now I've done it for the T00. So please check it. Like, it's a bit of calculation. You'll have fun, right? Just, I have defined all the relevant quantities for you, right? So just compute the relevant quantity and put that back in these volume elements. It needs to be demonstrated that it can be done, right? That's why I went through this exercise. A little tedious, but needs to be done, right? So our choice of coordinate system is pretty good. Like, we have chosen the right momenta. You see, it simplifies the expression inside this integral, right? Even though the definition of Q is very complicated, it is physical momentum multiplied by A, actually. It's a pretty complicated definition. Physical momentum is a complicated function of time. There are perturbation quantities inside of it, right? That's how physical momentum is defined. Remember, G00 in the linear perturbation theory, I've been defining 0, 0. So that's a complicated definition. So that is needed for our purposes. If I define coordinate momenta for our calculation, then I will be dealing with this complicated volume element. I can deal with it, right? One can deal with it, but it's much more complicated to do it. So now I'm left with T0i, Ti0, T0i is the same actually, and Tij, I not equal to j or the traceless component. But I don't have to worry about these two. Can somebody tell me now why I don't have to worry about these two? I computed these volume elements and showed they are independent of perturbation quantities, right? I did it for pressure perturbation, pressure. I did it for density, T00. But I don't have to do it for bulk velocity and the anisotropic stress component. Why do I not have to worry about it? The similar integrals will be there, right? Is that point clear to everybody? They're already first order quantities. So the background doesn't contribute. See, there is no contribution from background to this quantity, right? Nor is there any contribution to background for this quantity, right? For the background, this quantity vanishes. But there is a background pressure and there is a background density, right? So there is a mixture of, so when I write down these expressions and I put it in first order, all those need to, I'll have to separate the 0th order term from the first order term. Here, they are already first order. I'll write down these forms in a short while. So I don't have to worry about checking it because already, so this will also always come. So I will write down fx equals I'll call it n, okay, whichever. So I'm going to define this phase space distribution function as a background quantity plus a linear quantity. The background quantity is only a function of q, right? And this is the linear perturbation. So what actually happens when I'm doing 0, 0 and I, the pressure part, that this first one also contributes. But when I'm doing T0i, you can show for yourself that this first part of the integral vanishes actually, which is the way of saying that, in background doesn't contribute. So only the first order contribution, which is this quantity, remains. Then I don't have to worry about any first order quantity in the volume element. Right? Go on.
You are considering H is equal to 1?
I haven't even said that actually. Yeah, why do you want me to? Because you see, I'm actually assuming that phase space distribution, unless I define phase space distribution function, I really don't have to worry about it. Right? I haven't defined it. So if I'm going to use a phase space distribution function, generally it's divided by h cube. I'll put h equal to 1 there. Right? So if I derive Fermi-Dirac or something, but I haven't yet done that. So I've not made any assumptions. Right? These are volume elements. They're independent of that choices. Right? Yeah, there I'll have to define by h cube. When I define, if F0Q is defined as a Fermi-Dirac distribution, then this is defined as this is H, this is not H bar, right? So this is how you define it actually, you see, so that you get all the dimensionality right, you see. So, and good point actually you made, because I just wanted to discuss this briefly, the phase space distribution function. So let's stop here and ask the question about what the phase space distribution function is, right? I'm going to come integral over phase space distribution function. Let's first discuss the zeroth order phase space distribution function, which is given by, so we always have a neutrino in mind, right? Some kind of neutrino. That is a minimum modeling we have to do to solve cosmology, right? A massive neutrino and a massless neutrino. But this kind of a formulation that is being developed here and discussed here, this will be valid for all warm dark matter models, all kinds of other class of models, right? Which are actually close cousins of cold dark matter and not of hot dark matter, right? This will be true for all such models. Let's say we have a Fermi-Dirac statistics for neutrinos, right? What would be its distribution function, right? Is this the correct form, its distribution function? Let me rephrase the question. Suppose I'm looking at the distribution function of massive neutrino from early universe, right? This is a standard model neutrino, which decoupled close to a temperature of 1 MeV. Remember, standard model neutrinos, they decouple from the rest of the thermal bath at around 1 MeV, right? And this is their energy, right? But is this the form I need to use? So suppose I'm doing this calculation at redshift of 10 to the power 5. I never really do this calculation as early as 10 to the power 10, right? What would be the form of distribution function of this? Why? Why should energy be replaced by momentum? Everybody hear this. Why should energy be replaced by momentum? Neutrinos have become relativistic at what time? Okay, so they are become non-relativistic after decoupling from, yes, they were highly relativistic at that point. But I'm doing this calculation much later. I'm doing this, say, at redshift of 1000. Okay, redshift of 1000, the temperature of the medium is around 0.2 electron volt. Let's say my neutrino was 1 electron volt. Is it relativistic at that point? Then can I use this with Q? Who said yes? Please explain. Is this point clear to everybody? And this is a very subtle point actually. The distribution function of a freely expanding particle is invariant, and that's what we were talking about, weren't we? It is an invariant quantity, right? We were talking about it yesterday when we talked about Liouville theorem, right? Now the distribution function of this particle basically freezed out, it stopped interacting with other particles, right? Through weak interaction, it was interacting with neutrinos, photons, and various other quantities up to redshift of 1 MeV, up to a temperature of 1 MeV. At 1 MeV, its mass was 1 electron volt, so it decoupled at that point. And when it decoupled, it was highly relativistic. But subsequent to that, its phase space distribution function has frozen, right? What it means is Q scaled, like photon, for instance. You see the same thing we always ask, no? What happened to photons after they decoupled? They decoupled at a redshift of 1000. We see them today. But we talk about the temperature as if temperature, somebody asked, how does the temperature of photon gas forms? Everybody shout, oh, 1 by Z, it goes as 1 by Z. It was not even in equilibrium. It wasn't even interacting with anything. How did it fall as 1 by? It fell by that because actually it's the momentum of the particle which was decaying as 1 over A, right? And that ratio P by T has to be conserved because phase-space distribution function is an invariant after the photon decouples. Same logic applies to neutrinos. So yes, you don't have to use E here, you have to use Q here, right? For all times, there is no need to use E there. Even after the particle has become non-relativistic. Now that's the important thing. Because the phase-space distribution function cannot change just when it becomes non-relativistic, right? Because it is not interacting with anything. So this has to be replaced with Q. Is this point clear to people? I mean, you may be thinking like this is, but I urge you to go back and you can read Dodelson's book. Dodelson does discuss this a bit in his book, right, in the first or second chapter. But I think there is an even longer discussion in a well-known book from 1990s called Kolb and Turner, right, which you can actually read these kind of arguments, right, how these neutrinos, they retain this form after they decouple. Wanted to say something? Okay. So it's fine. Yeah, please. So by the way, so that actually it means that this ratio remaining the same, right? Q actually already absorbs the temperature change. So this should be T0, in fact. Q is already the co-moving momentum, right? So for actually the phase-space distribution freezing is that all these quantities are independent of time now. Otherwise, it would have been a function of a ratio of two quantities, both dependent on time. But our choice of coordinate also has ensured that it is actually a function of quantities which are both independent of time. Q is independent of time, and so is T0. So this is a phase-space distribution function we use. But having said this, it is very clear that this could be true of any other particle also. Suppose I'm studying warm dark matter. Okay. Suppose I'm studying warm dark matter and I have the same premise there, that this warm dark matter particle formed and decoupled from the rest of the thermal bath long before it became non-relativistic, right? Same logic will apply to that also, right? So even when we study warm dark matter models, similar kind of distribution functions are used. And the logic is exactly the same. There, the temperature could be different. The T0 for neutrino is fixed by, like we have already discussed it, right? That it's basically the decoupling happens and then electron-positron annihilation happens. Remember in yesterday's lecture, 4 by 11 factor came. That is for the standard model neutrino. But this would be true for any other particle also, whether it's a standard model neutrino or not. This logic is independent of that fact, right? It only depends on one fact, that it should decouple when it is highly relativistic. If it does, and it decouples subsequent after that, it will always be invariant. It will be invariant under expansion, and it will have this kind of a form. So all the papers that you would see for warm dark matter particle and all kinds of other particles, they all use this form, and for this reason. Okay. So now what I will do is, I'm wondering. I'll go back to the Boltzmann equation and try to write it in a form that we can solve it in. I had written this. Now we have chosen the coordinate. There was one more term that had to do with directions, which we argued yesterday is going to be second order, so neglected. I hope some of you at least went back and proved to yourself that dpi hat by d lambda is actually equal to 0 for an expanding universe at 0th order. Please check it if you haven't done that yet. Okay. Now what I need to solve this system I need an expression for this, and I need an expression for this. You can show so this again follows because dxi by d lambda is pi. This is the definition of pi, right? You should be able to show this, right? So pi has this following component, p mu. I leave this as an exercise to you. This actually, not just that. Am I using what notations am I using later? N is good. Sometimes I use N, sometimes I use P, right? But I'll put a hat when I use P, right? This is a unit vector in the direction of the momentum of the particle, right? So you should be able to show this. I'll leave it as an exercise for you, right? Show that these are the components of the four momenta, and you will get this. Dx by d lambda will give you this formula. Sorry, sorry, then. P0, you have to divide by P0. So, sorry, say it again.
1 minus 5.
Why should it be 1 minus 5? This is 1 plus 5, right? This is 1 plus 5. Check it actually. Check it. I think it's correct. Because dx by, sorry, so I'll just. Go fast. E0 will come in the denominator. Okay, just check it. There'll be a plus here. But wait, does it even matter? Like now the first question I ask is that I want to write this equation in the first order, right? I want to write this equation in first order. What is the order of this term? Is it 0th order? Does it have 0th order contribution? Does it get contribution from 0th order, this term? No, because f is not a function of x in the 0th order, right? F is a function of x only in the first order, right? So this is a term that first order by construction. So I have to take this term only in the 0th order. So all of these terms are not going to matter, not for my analysis, right? I can drop all of these terms, right? Let's try to compute this now. Now this is a little complicated. Actually, people who want to compute this, I will urge them to go look at Dodelson's book. Dodelson actually spends almost 2.5 pages of calculation to show what this comes to. Okay, it's a little complicated, but I'll urge you to go see it. Right? I'll write down the final formula of this without calculating it. dq, and I can switch to notation of Dodelson now. The tau is the proper time now. He's assuming a massive particle is always there, that you can always replace tau with lambda whenever you feel like. Make no difference to the calculation. This will require a bit of calculation to show that this to the linear order is equal to this, right? I'll urge you to compute it yourself, right? Now we are set. We have all the relevant terms in this equation. So we can now write down the equation in full. So I will use this expansion, the one I have written here, right? And I'll throw away the 0th order term. 0th order term, by the way, you can prove to yourself the f0 by d tau is actually 0. Right? It doesn't change. Right? It actually is a function of variables which are time independent. All the terms that really matter are the ones which are first order. So I'll write down the first order equation right here. I've also gone to Fourier space. What I've done is, first of all the derivatives, I've gone to Fourier space. They're replaced by this. So what I've done is, I've defined all quantities in Fourier space, right? So all the x's will get replaced by k. I'll not define that process, like I'll not discuss that process in detail. But I'm sure you're aware of the fact that linear problems are best solved in Fourier space, right? And for the system we have in mind, we have a 3+1 split of the in general relativity, right? And I have a spatial metric which is flat. So Fourier space is the best way to look at it. Fourier space is the language we should use when we are in three-dimensional Euclidean space. That's what it is, right? So I've gone to Fourier space. That's one thing. F0 is that F0. I think I'd write it properly there. I wrote it differently. That's a background metric. This is it. This is our master equation. This equals to 0, right? Somebody wants to comment on this equation. What kind of equation is this actually? It's a simple equation. It's not a partial differential equation. But is it a single equation? See, you can easily see this is an infinite set of equations for any given k. I want to solve it for any given Fourier mode k, right? That's my aim, right? But it depends on where the photon is coming from. So it depends on the magnitude of the momentum of the photon through this q. It depends on the direction of the photon, right? So it's actually not one equation. This is an infinite number of equations, right? Is this clear to people? Can they appreciate it? There's not one equation, right? These are infinite number of equations. I really not achieved that much by writing it in this form. I mean, it needed to be written, right? So now I have to like do something so that I can handle this equation. I can reduce it to a set of equations which are tractable, right? This infinite set of equations. One for each direction of photon, each momentum of photon, right? So let's see how we do that. I won't stop here. Do you have any further comments on this point? Is this clear to people? Do you want to have some questions now? Change tack again at this point. I'm going too fast. I want to finish something today. Last lecture. Okay, I'll move on. Now what I'll do to solve this equation, and this is a standard method used in solving similar kind of problem in a lot of physics, right? Is first I will deal with this angle. First I'll deal with this angle, and then I'll use this deal with this q, which is the magnitude of the momentum. And the way to deal with a single angle, if a physical quantity is a function of a single angle, the natural expansion for that is in Legendre polynomials, and that we know. So what we do first is to expand this psi in Legendre polynomials. Now it's a function of k, it's a function of n, it's a function of q, and it's a function of tau. And I'll write it as an expansion in Legendre polynomial. This quantity is not a function of the angle. This quantity is a function of angle. I can invert it using the completeness relation of the Legendre polynomials. Sorry, what to write the Legendre polynomial itself. What is it a function of? What is that cos theta equal to? K dot n. Let me write it as k dot n instead of cos theta, right? So there is an angle between the Fourier mode and the direction of the photon, and that's what this is an argument of. We are done, and now what we can do is we can expand, we can invert this relation using the completeness relation of Legendre polynomials, and how many eyes I used in this definition is entirely up to me. The quantities are defined in such a way that they are suitable numerically. If I let this factors of I hang in something I'm going to compute numerically, it's harder, of course, right? I want to use complex algebra for doing it. So this is just done to make numerical calculation easier later on. So this is my choice. Now I'll define mu as the angle between the direction of photon and the Fourier mode in question. Okay, so I want to deal with these quantities. So let me first define my matter variables yet again, right? So that I can deal with these quantities. I will want you to show the following, some exercise for you. I just want to say what I've done here. I didn't write the full form again. The density perturbation was a function of the first order perturbation, right? Which was this. This is the first order perturbation. There was an integral over an angle, remember? There was an integral over q and there was an integral over an angle. I have aligned my axis to the k axis. So to carry out those integrals, right, I have to integrate over all the angles, right? Q's, all the q angles have to be integrated, right? So, but I have the choice of aligning my k vector to the z axis. So so this cos theta is basically a k is z axis. So all the angles can be measured with respect to that. And if you can do that, you can carry out that integral. So when you carry out that integral, you define psi 0, which is this. Psi 0 is an integral over this quantity with L equals 0. L equal to 0 is unity. P0 mu is unity, right? So that way I can define my matter variables in terms of these moments. Now that's a trick. These moments, and you would see I don't need many moments. I only need a handful of moments of this, right? I don't have to solve for them. But well, when I solve this equation, I'll have to do a very complicated job, right? So density perturbation can be defined like this, and other variables will be defined similarly in terms of moments of this perturbed distribution function. I will simply write down this form and I'll let you compute it yourself. Is fairly straightforward from what you have seen so far. The factor of 3 here because pressure is defined as the trace component divided by 3. That's how pressure is defined. You take the trace and divide by 3. So that's where this factor of 3 comes in. So angular integral has been carried out here. But this is pressure perturbation. Okay, I'll write down the form and then define. First, I will define something called theta, which is I, Aj, Ej. So I'm going to define a divergence of a velocity. And this relation I will not prove to you. I'll leave it to prove to. You can try to prove it yourself. And you can actually do it using the perfect fluid form. This becomes equal to, so I can carry out this integral. Now there is a single angle sitting here, right? When I carry out this angular integral, this quantity. So I will have the first moment and I'll write down the first moment. 4 pi k A4 q square bq this is proportional to the first moment. I1 PL P1 mu is mu. That's what this n was. Now I'll talk about the most complicated of the moments, which is the anisotropic stress for the scalar modes. That is defined in the following way. So this projector here, Nij minus delta Ij by 3, this, so pressure is the trace part. This is the traceless part. So this I've added delta Ij. This was a Nij. I've added this part to make sure it's only the traceless part that is projected here, right? Based on this, I can define what is called so for scalar modes, there is only one component of this anisotropic stress that's useful to me, which I argued yesterday. Anisotropic stress has 5 components which are non-zero. 1 for scalars, 2 for vectors, and 2 for tensors. Only one of them is useful to me. I project it out by projecting it further with this, right? Which actually gives you the traceless component of the matter of the metric, on the left-hand side, the metric perturbation. When I multiply by this, it gives me the traceless component of the Einstein tensor also. I define this sigma, and this sigma is called the anisotropic stress. It's a single variable, and it is defined in the following way. So again, all this integral you multiply by ki, kj minus this, there is square of this quantity, and I'll let you work it out. It'll come out proportional to the second moment, the P2. Apart from that, some other factors. Let me identify now what all I've done. I've written a lot of things here. Let me just stop and summarize. What we have done here is, for solving the system, I need 4 quantities. I need density perturbations. I need pressure perturbations. I need bulk velocity, and I need anisotropic stress, right? In fact, I can deal with a fraction of these quantities because Einstein's equation overdetermined this, but I have to deal with fair fraction, I mean, at least 2 of them. Generally, if it's a multiple component fluid, all 4 of them. Right? Let's look at these quantities and try to make sense out of it. The density perturbation is important in all cases, right? And the density perturbation is weighted by this epsilon, right? So in initial time, this epsilon is just Q, so it's a relativistic particle. And later on, of course, when this becomes non-relativistic, this epsilon is MA dominates. Pressure, if you notice, what happens to pressure perturbation as you become non-relativistic? The pressure perturbation is suppressed when you become non-relativistic, right? Because the epsilon comes in denominator, right? Epsilon is m square a square plus q square. When m square a square dominates, this is suppressed. How will it go when the particle become non-relativistic? Not as 1 by a4, but it will go as 1 by a5. So the density perturbations, once epsilon becomes dominant, how does it behave? It is m into a, 1a cancel with this a, right? The density perturbation goes as 1 by a cube, while the pressure perturbation goes as 1 by a5. The pressure perturbations, when a particle becomes non-relativistic, becomes increasingly negligible. It is large in the past, but becomes small when the particle becomes non-relativistic. You can't draw any such conclusion about this perturbation, which is the bulk velocity perturbation. But let's look at anisotropic stress. Does anybody want to comment on anisotropic stress? When do you think will it be important? And when do you think it is negligible? Why? So perfect fluid, it's 0. Perfect fluid is defined to be 0, right? Clear. No, but suppose it's not a perfect fluid. It's a set of particles, right? Like neutrinos. When do you think it will contribute? It will have significant contribution. Which part of the evolution of the universe? No, just look at this formula. Don't think like this. So what did I just argue about pressure perturbation and density perturbation? I said pressure perturbations become negligible, right? They fall as a higher power of A when the particle becomes non-relativist. Think about particles, right? Don't think about matter dominated and all. Think about particles, right? Energy density could be dominated by another particle, right? What about this particle? So we have all the particles, they have different masses, they have like different distribution functions, right? So they all behave differently. But one thing is clear, there is again this epsilon is a denominator here, right? This is also suppressed when the particle becomes non-relativistic, right? So this is again the anisotropic stress is important. Both pressure perturbations as well as anisotropic stress is important when the particle is relativistic, right? They become increasingly, and this is true because you see one of the things that we want to, and when we are at it, one of the holy grails you can say of like, at least for some people, is to detect this anisotropic stress. So this anisotropic stress is actually 0 for CDM, that much is clear to all of you, right? Because for non-relativistic particle will be very small. Anisotropic stress is 0 actually, right? So is pressure perturbations, right? So these are not, CDM particles do not have it. Photons don't have it for another reason, because they're interacting with baryons, right? So they have very short mean free paths, they do not have it either. It actually is mostly coming from massless and very light neutrinos, right? And we want to actually detect it in a cosmological observable. Now, cosmological observable, this calculation is included, but to say that you can detect it is a hard thing, you see. Can you isolate the impact of this from other particles? It has not yet been possible, even though there are claims, right? So maybe one day it will happen. So the anisotropic stress contributed by the massless neutrino or a massive neutrino, which is making a transition from relativistic to non-relativistic just around the time of recombination. Maybe we'll get it, right? So this is one of the things we would like to understand better, right? So far, they have been claimed, there are claims going back to WMAP times, 2006. There's a detection of anisotropic stress from massless neutrinos, right? But again, it depends a bit on how you parameterize the system, so I'll not dwell on it further. But it's an important quantity to deal with. Similarly, if you model dark matter, and in a way where you actually put in a lot of anisotropic stress, right? It is relativistic for long, right? there could be implications for it on observable, right, from this term, anisotropic stress. So it's an important quantity. For most cases, it's neglected, right, for most of the non-relativistic particles. Relativistic particles, and when they remain relativistic for long, this is an important factor to take into account. But again, I haven't shown that it affects small scales, but I think I'll not have time to show that. So it's actually an effect on the small scale. So in fact, people are discussing galactic halos and various things today. One way people have tried to model even halos is taking into account this anisotropic stress. There is some literature in the past, but that was on slightly larger scale, like clusters of galaxies, to see if you can see the impact of this in an observable. So far, it's not possible. Like I said, I don't believe it will happen on those objects. But this may happen in linear theory in CMB data. Okay, now that we have defined this, let's work with this equation now. Let's try to make sense out of this equation. What we can do to this equation is, we want 3 moments of this equation. We want psi 0, we want psi 1, and we want psi 2, right? That's all that we need. I don't need higher moments. Once I have these 3 moments, I can solve Einstein equation and I can get my better variable for solving Einstein's equation, right? But let me take those moments and not give you too much of details, and I'll invite you to work it out yourself. Let me write down the form that we get. So this I can wipe, no? So what you do is you take this equation, you multiply, you first take an angular integral of this equation, right? So when you take an angular integral of this equation, you can see that this will give you a psi 0, this will give you a psi 1 actually, right? Because there's an n sitting here, right? And these quantities will give you nothing more, because an angular integral over these will just give you unity. They do not depend on that angle, right? This psi and this phi do not depend on the angle at all. They depend only on they are the potentials, which are not functions of momenta of particles, right? Only these quantities depend on it. So let me first write down the 0th moment. This is the 0th moment. For computing the first moment, multiplied by mu now, which is k dot n, and integrate this first one, and you have to multiply by an I also. The convention I'm using, please go back to the convention, right, to compute it, the first moment and all. So I'll retain all those I's. That gives you so here, for instance, when you multiply by, the first term will go to 0. If I multiply by n and integrate over angles, this first term will go to 0. The second term is going to contribute there. The first 2 terms, one of them is going to give me a combination of psi 0 and psi 1 because it's mu square. So I'll split it into Legendre polynomials of 2nd and 0th order. Let me write down the final term now. All these potential terms will actually vanish once I start taking the second moment. If I multiply by P2, the first term will go to 0 because P2 first term, P2, P0 will give you from orthonormality will give you 0. This is P1. Once I multiply it by P2, this will also be 0. So all of these potential terms will go to 0. So all the terms which are L greater than or equal to 2 are fairly straightforward. Right? I had derivation in my notes, but I don't have time to do a complete derivation. But I wanted to do this. Right? If you are like keen on understanding some of these things, do this derivation, all of these moments actually. How many equations are these? These are again infinite number of equations, right? Which is what you expected. You started with an infinite number of equations, and you still have an infinite number of equations, but in the moments, the angular moments of the distribution function, right? Let's first stare at this equation and try to make sense, some sense out of it, right? What do you expect minimum from these set of equations? Whatever else we have discussed so far. If the particle was non-relativistic, do you think what will happen if the particle is non-relativistic? Speculate. Remember, when particle was non-relativistic, I didn't have to solve these equations, right? I could have, if the particle was totally non-relativistic, I could have used perfect fluid approximation, which would have given me one equation. One equation for density, another equation for velocity, and then nothing else, right? So clearly, when the particle is non-relativistic, this equation should reduce to simpler form. Can you see it? Why? Why? Okay, so let me ask you the question. Suppose the particle is highly non-relativistic, right? What will happen to this set of equations? It's an expansion in Q by epsilon. And that epsilon, yeah, it's actually much larger than Q, right? Again, let's recall what epsilon is. Right? So when the particle is highly non-relativistic, it is this term is going to dominate, which is going to become larger and larger as time passes, right? So this expansion is an expansion in Q by epsilon actually. When Q by epsilon is much, much smaller than unity, right? Then you can see that every subsequent moment actually is so if I do the second moment depends on the first moment and the third moment, right? So if I want to compute the third moment, and there is a Q by E factor sitting outside. So the second moment is Q by E of the first moment. The third moment is Q square by E square of the first moment, right? The fourth moment is Q cube. So it goes, right? So when Q by E is small, every subsequent moment is smaller by a factor of Q by E. So indeed, my equations will be simpler when the particle is highly non-relativistic, right? I'll be dealing with just these two equations, right? And I will show you that when you integrate these equations now over Q under those limits when the particle is highly non-relativistic, it gives you the same equation you get for CDM from the perfect fluid approximation. So this is a completely consistent picture. Is it an expansion in something else? It's an expansion in Q by E. We have established that. Is it? Do this equation show something else? It is BBGK hierarchy. So what is it an expansion in? It is an expansion in Q by epsilon, right? But you see, when you said BBJK hierarchy, that what was that scale in the problem there? It is BBJK hierarchy. Identify that scale. What is BBJK hierarchy in? BBJK hierarchy is an expansion in actually some length scale in the problem. Okay. This is called BBJK hierarchy. It's named after 5 people. BBGKY. I mean, I don't know what those names stand for. I think like, anyway, you can figure it out. Right? You can search, right? Basically, you start with the distribution function of a collisionless plasma. These are the same equations of a collisionless plasma. You start with distribution function, and you take the first moment, that gives you continuity equation. You take the second moment, that gives you Euler equation. But now it is coupled to the second moment. You get the second moment, it doesn't have a name. Maybe it has a name, I don't know. But so it goes. The whole aim of solving such equation is to truncate. So there is a big area of research in plasma research. It's called truncating BBJK hierarchy. You have to identify a length scale to truncate it. Okay. We haven't identified that length scale yet. All we have identified is that our common notion was that when the particle is non-relativistic, I should got only two equations, which we have proved, I think. But we haven't yet identified that length scale. What is that length scale in the problem? What is the length scale in cosmology? Hubble, you said Hubble? Hubble when? 1 over k also? 1 over k when? No. Be clear. What time? We are not dealing with that situation here, right? What is the scale in the problem? Yeah, horizon is the scale in the problem, right? Horizon. So what dimensionless number do I take to see if there is a truncation of this hierarchy? I need a dimensionless number. K by h? People agree? Huh? Sure, don't worry about C's. C's we'll put in. You're right. But you see, K is co-moving. But we have already defined a quantity like that. Eta. Don't say K by h, say K eta. You already have eta is 1 by h, is co-moving, right? Integrated, right? So K eta is the dimensionless quantity we have already actually defined in our problem, right? So is this the dimensionless quantity? Is this an expansion? Is that dimensionless quantity? See, let me try to understand. Let me try to explain to you how BBJK hierarchy works. And then you will have a sense. BBJK hierarchy is an expansion in generally the mean free path of a particle in a plasma. It is called a plasma, which is like collisionless, but nothing is really collisionless. There is a scale in the problem. So what you do is you expand in the mean free path of that particle. There is no mean free path here, right? Particle is here genuinely, I mean, it's free streaming, right? So the only scale in the problem is the horizon size, right? Eta. So K eta of unity is when it enters the horizon, right? Correct? Like I said yesterday, all the mode starts from way outside the horizon, right? Can you identify that scale here? Can you truncate it under certain condition when K eta takes some form? Can you? Yeah, tau is of course tau is eta. Sorry, like let me put tau here. Tau is eta. I'm sorry. I mean, this is my mistake. You see, I'm using. So you see, if psi takes the form of some power law, right? This is k tau, isn't it? No, it's like every higher moment was q by epsilon. Every higher moment is also k tau smaller, isn't it? So it's an expansion in two parameters. One to do with whether the particle is relativistic or non-relativistic. One to do with whether it's outside the horizon, the mode, or inside the horizon. When the mode is outside the horizon, k tau much smaller than unity. These terms are negligible, right? Because this is an expansion in k tau. And I can compute this, so I can take a power law solution for this, which is true actually in the past. And then I can show that this is indeed an expansion in k tau. Every subsequent moment is smaller by a factor of k tau, right? So when we start in the early universe, we do start, so everything behaves like a fluid. Why does everything behave like a fluid? Only these two equations matter. This is again, so there is no difference between cold dark matter and hot dark matter or a relativistic particle in the early universe. Why is there no difference between those two? There's no difference between the two because the difference comes from the mean free path of those particles. Nothing at scales which are larger than the horizon size, all particles behave like an ideal fluid. And that's what this equation is showing you, right? So when they are non-relativistic, it decouples whenever they become non-relativistic. But they also behave the same way when the mode is way outside the horizon. By the way, this is another reason why CMB anisotropies are difficult. It is difficult to distinguish between hot dark matter and cold dark matter using CMB anisotropy measurement at large scales, you see. Because at large scales, you see, these terms are not playing such an important role. They start playing a role at smaller scales, right? So they are not a great discriminator of massive neutrino for that reason, right? And we know that. I mean, we need to get lensing, we need to get BAO, right? CMB is such a great probe of everything else, but not of this. And this is part of the reason. Okay, now let's solve these equations, right? Let me see how much time do I have. Roughly 20 minutes. Okay, so now we have established that these set of equations, these are infinite hierarchy of equations. We have no natural way of truncating it except when they become non-relativistic. Particles do become non-relativistic, right? But when they enter the horizon, so all the modes like I showed, they all enter the horizon. As particles enter the horizon, all these terms become important. They are less important when they're outside the horizon. After horizon entry, in fact, these terms start playing an important role. You can probably truncate it if your Q by epsilon has become small. Right now, we are dealing with a situation which is not entirely straightforward because we are dealing with neutrinos which are around 0.1 electron volt. So by 0.1 electron volt, they are barely becoming non-relativistic at recombination. They have a substantial effect at much, much lower redshifts. And when k tau becomes on the order of 5 or 6, right, these terms dominate. And you go to higher and higher order. So what actually happens is that initially it is the lower moments that dominate. You start way outside the horizon, start evolving these equations. The lower mode play an important role. Then the larger and larger modes, once your horizon entry happens, start playing a role. So we still have to find a way to truncate this, and I'll briefly discuss it. But let me first write it in a form, break it for you for massless neutrino as well as massive neutrinos. You see, they are still function of Q. I still haven't dealt with Q. I still have to deal with Q, right? So if I cannot deal with this Q, notice what I have to do. I have to solve these equations. I have to carry out these integrals, by the way, numerically. Okay. It's a pretty complicated problem in computer. And you have to carry out this integral at every time step. And then put it on the right-hand side of Einstein equation and solve it. But for certain cases, I can get rid of the Q dependence. And one such case is, of course, when the particle is massless. So let me just deal with that case. That's a massless neutrino. Where do I have it? Here I have it. For massless neutrinos, Q is epsilon, right? Sorry, epsilon, yeah, epsilon is equal to Q, right? Because M is 0. This actually cancels from here. This cancels. What I can do is, I can actually integrate these equations in a fairly straightforward way. I will put epsilon equal to Q, and I will integrate these equations now over momenta to see if I can reduce it to a more tractable form, because I don't want to compute these integral over momenta numerically, because that's a mess, right? So let me do that. I'll define first delta nu as delta rho nu by rho nu bar. And I already have shown you what form it will take when epsilon equal to Q. I'll not read down these forms. You can write similarly thetas, you can write sigma. And these are the equations you get once you put Q equals to epsilon and you integrate over the momentum. equations look neater, right? All the Q dependence is gone now. I've defined it in terms of these two equations indeed are continuity and Euler equations, right? Now you can recognize, but this is not an Euler equation because Euler equation, the sigma nu would go to 0 in an Euler equation, but that doesn't go to 0. So it is coupled to the higher moment, and sigma nu is the second moment, right? It is related to the second moment as I defined before, right? And it's still an infinite hierarchy of equation. I mean, the equation number of equations is still infinite. Now only the Q dependence is gone, right? These, go on, please. Which one? Okay, wait. I'll define it. You see, because I'm eating some step for my note. F nu 0. This is the highest. So this is basically, I'm defining Kn. So I have defined higher moments of the phase space distribution function as f's. Okay. So up to first order, I've defined thetas. Now f, so this is f is sigma is half. The sigma is defined as just half of this. The second moment is sigma. So I could have written a sigma here, but then I'll have to write another set of equations, right? So f is basically the higher and higher moments of the phase space distribution function. Still an infinite hierarchy of equation. And when you solve it, so this has to be solved numerically. There is no way around it, right? You can only do so much because you see, there is no way to truncate it further. There is no scale remaining in the problem, right? The non-relativistic part, that's gone. So of course, there is an expansion in k tau, the beginning of the universe, and long ago. Initially, these moments do not contribute. We start with an initial condition where only these two equations matter actually. But finally, as the modes enter the horizon, they start playing a more and more important role. So in fact, when CMB codes are written, you have roughly 10 equations corresponding to photons, baryons, cold dark matter and all. And you have around 25 equations for massless neutrinos. That's simply solved. You have to truncate this hierarchy somewhere. I mean, there are no easy way because there are no scales in the problem. So that has to be done a bit by hit and trial. Okay. So when people write codes, they just check, okay, 10th moment. Right? I was working with a student and he was doing it. He told me 6th moment sometime works, sometime 8th moment works. So the whole point is, it depends also on the other matter components. And we take the most conservative choice depending on the kind of precision we want in the numerical code. If you're looking at a code like a few % precision, then you'll have to retain around 15 equations of these. Solve it. And then there are ways to truncate it. I'll not go into the details of how to truncate it. There are ways to truncate it, but like I said, there is no scale in the problem here, right? So there is no natural way to truncate it. Only thing that happens is that neutrinos are subdominant. All the neutrinos together contribute only 40% of photons. And when matter domination starts, after that, these neutrinos become even more subdominant because matter dominates over radiation. So over a period of time, whatever perturbations neutrinos are creating, they play a smaller and smaller role. So the relative errors that you incur by neglecting this become smaller and smaller. Okay, if this was the one case, let me derive the opposite case. So I have a discussion here on truncating the hierarchy, but I'm running out of time. So I'll just show you the other case, and then I think I'll stop. CDM. What happens when you have, you have an approximate idea anyway about what will happen when epsilon is on the order of m into a. When epsilon becomes on the order of m into a, that is the CDM case. And you see, this is an important limit to derive because this is what actually happens when you are dealing with warm dark matter particles. The whole range of particles that people are studying now, they are changing phase space distribution functions. They are changing the mass of the particle, they're changing the temperature of the particle, they're doing all kinds of the gymnastics with it. Same set of equations are used there. But you can actually figure out what limits I work it in. So I'll work out just an extreme limit. When epsilon is m into a, right? Then these are negligible, right? That we already discussed. So I can drop this. What you can do is, These two equations now I have to take moments of, right? And I have to demonstrate to you that these actually reduced to the CDM equations, which by the way would be the same equations without this epsilon. And there will be a factor of 4. I think there will be a factor of 3 here somewhere. There's a 4/3 here, and this will be 3. Right? There's one factor, additional factor comes for massless particles. Let me just go through this procedure briefly and write down the final equations. I'll not give you details. You can actually multiply this equation with, I'll just give you the steps. The first equation, multiplied by epsilon first, and then hit with 4 pi by A4 EQ Q square naught integral. Once you carry out this integral and manipulate all the expressions, get the final equation. There was a 4 phi here, 4 phi here. You see the only difference between these two equations is 4 has become 3 because it's a non-relativistic particle. This should have been 3, so 3 cancels with 3. So this is an equation for CDM particle. This is the first equation. And the second, take the second equation, the third is negligible, and hit it with the following vector. You have to work through the details. In fact, you have to show that this term is indeed, the entire term is subdominant because it's 1 by Q, 1 by epsilon, right? This entire term is negligible in that case. That one contributes. And what you get is, implies, like I just write down the equation. This is the second equation. These two equations can be derived actually from Einstein's equation using a perfect fluid approximation, right? For equation of state of a particle of W equal to 0, if you take W equal to 0, drop all pressure perturbations. This equation can be derived in that approximation also. I've come by a longer route. I've come by a longer route because I wanted to convince you that that is the most general route to the problem, right? Today, when we are trying to understand if, like, we have fuzzy dark matter, we have warm dark matter, we have various things. Linear perturbation theory, there are many calculations which are being done like this. These things are generally incorporated into numerical codes. But one thing I know from my own experience and working with students is that when you go inside the code, you have no idea what you're dealing with unless you have figured things out analytically, right? And this is the level of understanding you would require if you want to go inside the code and be able to change it confidently and work with it, right? So that is what you deal with. These are the most general equation you deal with. And what I try to show is that there are two limits. One is the massless neutrino, and the other is the very massive particle. Generally, we are somewhere in the middle. So when I introduce a new exotic particle in my analysis, then what I'm doing is I'm working with this. Maybe in some cases, this is not negligible. It's possible, right? But this is an extreme case of CDM, right? So generally, CDM is the easiest thing to deal with in numerical codes because there are just two equations there, right? And the hardest by this time you have surmised to deal with are massive free streaming particles, right? Who make a transition from relativistic to non-relativistic, right? These are hardest to deal with. You have to solve for this case, at least 25 equations have to be solved, roughly. So like, for instance, a code like CMB fast will solve around 55 equations, right? When all of these complications are, when massive neutrinos are there. But not only that, you have to actually do an integral at each time steps or momenta also. So if any of you actually have played with these codes, right? Do first a case, like go and run it, and you run it first with 0 mass for neutrinos, and then you give a small mass and rerun it. You'll see like there's a perceptible difference in the output. Output becomes much, much slower, right? And one of the things we also do in writing our own codes is to speed them up, right? Because when you want to do compare with data, right? If the code takes a long time to run, then comparison with data becomes harder. You know, the codes run for days. So that is another way to how you actually deal with this stuff. How do you actually deal with that stuff? So this is the game. I wanted to cover a few other things, but I knew I'll not have time. So I think I'm not done, and I don't have time to do anything more. I wanted to cover a few more steps, but I think I'll take some questions now. Yeah, I have time for questions. Go on. Went too fast today. Wanted to cover a few things. Some comments. Yeah, of course. I don't have PDF forms notes actually, but I can look at this guy, right? First thing he asked, why did you come to lecture here? I could have sent you my notes only, right? It's okay. No, I don't. I have in my handwritten form. Huh? Yes. The whole point is, yeah, but you see, there are many steps I have missed.
Yeah, that's
right. Okay, sure, I can, but I don't have. I can scan it and send it to you. Yeah, I can scan it. I can scan it and send it to you. You can see the details there. Sure. No problems. Yeah, these notes are meant to be shared. Go on. Okay, so it's a good point actually. You see, by this time even I'm forgetting what I was doing, but let me say it anyway. So point is, what was our aim in these 2 lectures? We wanted to cover a specific aspect of the problem of cosmological perturbation theory. And the specific aspect was to look at the dark sector, the sector which is made up of neutrinos, both massless and massive, as well as cold dark matter. Those are the 3 components which I wanted to discuss in detail. That was my aim from yesterday. We set up that problem, right? We talked about cosmological perturbation theory, like, how the metric perturbations evolve, scalar perturbation, vectors, tensors, and stuff like that. At the same time, we developed Boltzmann equations for solving this problem, right? To convince you that Boltzmann equation is the most natural way to look at this problem, right? So we set a Boltzmann equation. And what I've done today is to show you how do you deal with these 3 components in the dark sector in the perturbation theory. The most complicated is a massive neutrino, which makes a transition from relativistic to non-relativistic. Right? I showed you on the one hand, there is a limit to it, which is a massless neutrino, which is always relativistic, right? And the other hand, you have the limit of a cold dark matter particle. Right? So I basically derived this. If I had time, I would work out consequences of these equations with you, right? Which I do not have. So what I have done in these 2 lectures is to basically work out in detail relevant equation for studying the dark sector in the universe. I have done this for the following reason, because you see, many of you, and these days, like, many people are looking at the problem in various, for instance, you can have a warm dark matter particle. You can have a particle which remains, which is a decay product of something, right? All of these problems are subset of problems of this in some way. You can deal with it. Suppose I give you a different distribution function. How do you deal with a different distribution function? Right? These days, there are many models for the distribution function can come from another physical process. It's non-thermally produced, they are called, right? So this prepares you to deal with some class of such problems, right? So without my lectures, if you went and looked at a numerical code which deals with this problem, you'll faint. What in the world is going on here, right? Now, I think you will get to that with greater confidence. It is a complicated problem. It's a complicated set of equations. That's what I've tried to convince you. So when people go and look at these codes, and I have some experience working with students on this. First time when I tell them and how they behave, and then after a few months, like, demeanor has changed, right? Also, we have discussed about it. It is to partly prepare you to deal with similar kind of problems. And I think I've convinced you it's not a straightforward problem also. There is problem starting from how do you choose variables for the problem, right? You have to deal with correct variables to start with, right? And then you have to solve this complicated set of equations and deal with them correctly. Understand whether you can actually truncate this hierarchy, when the hierarchy can be truncated, when it cannot be truncated. There's a fair amount of literature on it, of course. Like, there are hundreds of papers on this subject, right? So this will prepare you to read some of them and make sense out of it. But yeah, I wanted to do more, but 3 hours, like, it's not possible. I think I've already done far more than I would do. Normally, I would cover what I did today in, nearly twice as much time. But I wanted to cover something. So sorry about that. I went too fast today. Yesterday I went slow, right? But I hope you got sense out of, at least a bit of sense out of it, right? Any further questions you have? Sure, go on. Yeah. Okay, first we'll come back to you. Yeah.
So, if we want to implement any new particle component in the radiation area, then we have this whole prescription.
Mhm.
If we want to implement an extra field, like something like an extra scalar field, then how much of this carries over?
Not much. That has to be done separately. A scalar field, when you're introducing scalar field, you generally have to start with the Lagrangian actually. Okay. Scalar field is a different beast. I cannot cover that. Yeah. So when you
we
look
would
at
still use the Boltzmann hierarchy for the photons and neutrinos and I mean all
so
the
in
standard
fact,
components.
yes, true. At least that part is there. So at least from this lecture, oh, by the way, CDM will be there. CDM will not be there. CDM will be replaced with say scalar field, right? Like ultralight axions. But massless neutrinos are there always in the problem, right? They have to be dealt with. So at least that part is common to all the other problems you will do. But if you want to do with scalar fields, right? Scalar fields like you have to start with Lagrangian and set up initial conditions which are pretty different from what we deal with here actually. So I worked with scalar fields. So yeah, it's a different thing. This is suitable if you are dealing with particles which make transition from relativistic to non-relativistic. All class of problems which deal with this paradigm in some way, right? This is suitable formulation. But at least one part of the formulation is suitable to anybody, which is neutrinos. The massless neutrinos have to be dealt with, you see. They are there in every single problem you can deal with. Okay. Yeah. Sorry. Okay. Go on. No. Well, I mean, these equations won't change because the Boltzmann equation, the right-hand side, there'll be a collision term. Right. And we do that when we do with photon baryon system, we do that actually. So, yeah, you can do that actually. For instance, like when you have dark matter. So, I mean, I worked on a problem one time where the dark matter was actually a neutral particle, electromagnetically interacting. It was actually interacting with photons. So you have to do that problem. So the point is, yeah, you add a right-hand side term to the dark matter and you have to deal with it. And you have to solve those equations. Yeah, sure. Interaction will mean additional terms actually. Absolutely, it will work exactly the same way, right? For instance, if it is a light particle, which is interacting some way with each other. See, we do the same for photons. You see, if I had done with photons, then you would have seen, we take the moments of both sides, right? So photons, it works. So it works for every particle actually. So for that case, we worked, of course, because the nature of interaction was such that it reaches equilibrium later than before. So it is decoupled in the past, but it gets coupled. Coulomb scattering has that property that it gets coupled because it goes as 1 by V4. When the particles become colder, they couple. So it was an interesting thing. But yeah, it can be dealt with. All kinds of problems like those can be dealt with. Yeah. She had a question. Can I take and come to you? Okay. You wanted to say something? Go on. First, finish your question. Yeah. Just 1 minute. Yeah. Yes. I derived an equation for massive neutrinos actually. In one limit, it goes to CDM. In one limit, it goes to massless neutrinos. You can derive both from it. The equations are general. See, that was the whole point. The equations are general, right? So they deal with an arbitrary particle of arbitrary mass and expansion history in some way. Right? So it starts non-relativistic, it becomes non-relativistic afterwards, right? CDM is always non-relativistic for relevant redshift range, so you can replace it epsilon with MA. Massless neutrino is always relativistic. So I showed to you that you can actually derive both those limits from this equation, right? Yeah, please go on. Yes, you're right. So you see, when you add an effective which is separate, right? So suppose you added one extra neutrino degrees of freedom, right? If it has the same temperature as the standard model neutrino, you are in trouble, because you see that is a problem. You will get into problem with both nucleosynthesis bound as well as CMB bound, right? We discussed CMB bounds yesterday, right? You can't add one, but you can add. So that's why ineffective it is called. Suppose I added a degree of freedom with a smaller temperature. So suppose my temperature of neutrinos today is 1.92 electron volt, not Kelvin, sorry, not electron volt, sorry, that'll be too large. Suppose I added a degree of freedom, 1 degree of freedom, but whose temperature is half of that much. Because the number density of neutrino goes as T cube and half the temperature, it actually contributes as 1/8 of a degree of freedom. In the final equation, it only adds as 1/8 of the degree of freedom, even though I've added 1 because the temperature was half. That is how we deal with it. If you add a non-relativistic particle which is not thermally produced, for instance, finally, our equations are not sensitive to how many degrees of freedom are there. They are sensitive to what is the total radiation content of the universe, right? So long as you keep that under control, you're okay. You integrate over whatever distribution you have, like your whatever momentum distribution, integrate over and says how much has it contributed to the radiation content of the universe, right? Roughly, you can change it by 10 to 20%. For nucleosynthesis, you can change by maybe 30%. CMB again, maybe 20-30%, give or take 20-30%. You can change by 20-30%. You can't change by more than that. You can't change by 50% or above for sure, right? So rest is up to you, right? The physics is not sensitive to how many, but what's the total radiation content that you have to add. Your model, you can have many models in mind for doing that, right? Okay. Any further questions, comments? One, please. Whenever something is a function of one angle, Legendre polynomial is the most natural language, right? If it was a function of something on the sky, we would have used spherical polar harmonics. So this was, you see, it's an important question actually. In scalar perturbations, the perturbations depend only on the dot product of the momentum of the particle and the K mode. So in fact, it is a function of just one variable out of the 6 we can. So it actually reduces the phase space, the dimensionality of phase space. So all the equations that I've written, it is because of the fact that we are dealing with scalar modes. If you're not dealing with scalar modes, this will not happen. Then we are dealing with a far more complicated problem. Okay. But in scalar modes, we can reduce everything is a function of a single angle, the angle between the direction of the particle and the K mode. So because it's a function of just a single angle, Legendre polynomial is the most natural language for it, right? If it was more complicated than that, we would use suitable, for instance, for studying polarization. We don't use this, we use other harmonics actually. Because there, this language changes, right? I can't use this like aligning, like I said, like I align my Z axis to K space. I can do it only under certain conditions. Here I could do it, scalar perturbations. So yeah, Legendre polynomial, just the best, the most convenient choice. Right? I have given some references. Mine Bachingar reference I have given. Also some other reference, and maybe I can scan my notes and send to everybody. You can do that also.